Number 16. If alpha is even, even means it's an even permutation in the symmetric group of degree n, because we are solving exercises on permutation groups. So if alpha is an even permutation, then we have to prove that its inverse is also even, and like that, if alpha is odd, then so is its inverse. Solution. So right at the beginning we use the definition of evenness of a permutation. A permutation is said to be even if it can be expressed as a product of an even number of two cycles, transpositions. So we start like this: since alpha is even, there exists transpositions, or okay, we should have mentioned the evenness. There exists an even number of transpositions A to n, or let us take a 2m, A to m, where m is of course a positive integer. No need to write that, that is understood, such that we do have to prove two things. Now if alpha is even, then this okay, so it's better to not start with things, start with if alpha is even, then there exists an even number of transpositions whose product is alpha. A to n, B to m. Then alpha inverse is the inverse of this Now we know that in any group, when we take the inverse of a product, that equals the product of the inverses of the individual factors in that product, but with the order reversed totally. So that is, this is equal to A to m, B to m inverse, and then after that let's just write the one that appears here before this one, A to m minus 1, B to m minus 1 inverse, and so on, A2, B2 inverse, A1, B1 inverse. Now we know that the inverse of a 2 cycle or a transposition is the 2 cycle itself. So alpha inverse is also expressible as a product of an even number of two cycles. So that is also even by definition of evenness. Hence, alpha inverse is a product of an even number of transpositions. Showing that it is even. And just like that, we have the odd case also. Let's just complete it without leaving it hanging like this. If alpha is odd, then there exists an odd number of transpositions. This time let us use the letters C and D. D2 C 2m minus, we have already taken m here, there. Let us take k. Where k is a positive integer, such that beta is their product. Oh, sorry, alpha. Where is beta coming from? We are still dealing with alpha, but now alpha is odd. Now take the inverse. Thus, alpha inverse let's write the one that appears here in this product before this one. Thus alpha inverse is a product of an odd number of transpositions. Showing that it is odd. That's the solution. Next, proof theorem 5-6. And this result states that the even permutations in Sn, in fact, let's just recall the statement. The statement is just this: the set of even permutations in Sn forms a subgroup of Sn. The theorem states that the set of all even permutations in the symmetric group Sn forms a subgroup of Sn. Okay, so to prove this, let us denote this set by something. Let An denote the set of all even permutations in Sn, since the identity permutation, which does not change any symbol, any of the n symbols, that is an even permutation. It is in An, and hence An is non-empty. Only when a subset of a group is non-empty can we ask the question whether it is a subgroup. The empty set, it cannot be a subgroup by definition. And if you are wondering exactly how the identity permutation is an even permutation, you just consider this thing. If you have the identity permutation, then it can be written as the product of these two cycles. Since it's a 2 cycle, its square is the identity, and in this representation there are two cycles, 2 transpositions, and that number 2 is even. So by the definition, E is an even permutation. That's it. So E belongs to AN. Now because Sn is a finite group, we know from a previous result that to prove that AN is a subgroup of Sn, it's enough to show that AN is closed under the product that we have in Sn. Since Sn is finite, it's enough to show that AN is closed. For that, let us take 2 elements in AN. Let sigma and tau be 2 elements in AN, then each one of them is an even permutation. Then there exist, because they are even permutations, each of them is expressible as a product of an even number of transpositions. There exist transpositions. Let's take them like before. A2, say S B2S, and then C1, D1, C2T, D2T, where S and T are positive integers, that is understood, such that and tau is this. Then you can see that sigma tau, sigma composition tau, whatever permutation it is, it has at least this representation as a product of transpositions, which has all these things. A2S, B2S, C1, D1, C2D2 C2T D2T. So you can see that in this representation also there are an even number of transpositions. Already we had we had how many transpositions here? 2s, and here in this for tau we have 2t transpositions. In sigma tau, in this representation we have 2s plus 2t transpositions, which is also an even number because sum of two even numbers is even. So that is why sigma composition T is again an even transposition, even permutation. Since 2s plus 2t is even, we have, instead of saying sigma composition T is an even permutation, the same thing can also be expressed like this more compactly, and that's what we wanted to show, because this alone implies, because our original group is finite, that An is a subgroup of Sn. You already know why it is denoted An, alternating group of degree n. That's what it is called. Note that the odd permutations will not form a subgroup, because that set will not have the identity permutation. So in these few exercises, we are looking at the nature of evenness or oddness of the product of two permutations whose own evenness or oddness are given. Okay, so then the next one, 18. In Sn, let alpha be an R cycle. Beta be an S cycle. And gamma be a T cycle. These R, S and T, these are lengths of these respective cycles. Complete the following statements. There are two statements. The first one is this: the composition alpha beta is even if and only if R plus S is ... that we have to write, and the composition alpha beta gamma is even if and only if r plus s plus t is this. Okay, so in a previous problem we already saw that if an n cycle, if we have an n cycle, okay, so we are considering Sn, no? So an m cycle, say, where m is of course less than or equal to n, and m cycle is even if and only if m is odd. So we are going to use that. So here we have an R cycle and an S cycle, I mean for the first one. So this is even if and only if. Okay, so what will R plus S be, that we have to figure out. Because we have two cycles, alpha and beta, these are not arbitrary permutations, they are specifically cycles. So let us proceed like this. Alpha beta is even if and only if either both alpha and beta are even or both alpha and beta are odd. Both the cycles becoming even and then the product becoming even, that we have seen here. Just like that, if you think of the other situation where say sigma and tau in the previous exercise are both odd permutations. Okay, so these products, these two products, each one of them will have an odd number of transpositions. So in this representation of sigma tau, how many transpositions will be there? This many transpositions plus this many transpositions, where in both the cases we have an odd number. But when you take their sum, odd plus odd becomes even. Okay, so that is why when either both alpha and beta are even, like what we have here, sigma and tau are both even, then of course sigma tau or alpha beta is even, but they are also even when both of them are odd. And if one of them is even and the other is odd, then in the one which is even, in its representation as a product of transpositions, there will be an even number of transpositions, whereas the similar representation for the other will have an odd number of transpositions. So when you take their composition, in that you will have an even number of transpositions plus an odd number of transpositions, which gives you an odd number of transpositions. So in that case, alpha beta will not be even, it will be odd. So that is why we write if and only if. Okay, if these things are true, then alpha beta is even, and that is the only case in which alpha beta can be even. And we continue, if and only if okay, now comes the thing about these cycles. When are the cycles even and when are they odd? Alpha is an R cycle, beta is an S cycle. Alpha is even if and only if R is odd. Okay, not even. So if and only if, just like that we have the S cycle beta. alpha and beta are both alpha and beta are even, so that corresponds to this if and only if both R and S are odd, or both alpha and beta are odd. That will happen when both R and S are even. Now, when both R and S are odd, then R plus S is even, and when both R and S are even, of course, then also R plus S is even. And these are the only two ways in which R plus S can be even. If one of these is even and the other is odd, then their sum is odd. So that is why we can still continue if and only if R plus S is even. Okay, so R plus S being even is necessary and sufficient for alpha beta to be even. But then there is that other one which involves 3 cycles, alpha, beta and gamma. Okay, so this will be more complicated. Cases will arise now. We will see. Let us start. Alpha, beta, gamma. Oh, but can we use this one to say something about this? Yes, I think we can use this here in this case. So let's just proceed like this. Alpha, beta, gamma is even if and only if what I am trying to do is to directly use this result. Can I do that? That's what I am thinking. We can view alpha, beta, gamma as a product of two. Oh, okay. No. We cannot use that here, because although we can interpret this as a product of two permutations, one of them is a cycle but the other is not necessarily a cycle. No, it's a product of two cycles. So this does not exactly, it does not exactly look like this case. So we have to do it separately. Anyway, I thought we could save a little labor. But anyway, alpha, beta, gamma is even if and only if we have to carefully see what the cases are. All of them are even. Are all even or. Oh, so this is again ultimately it's going to be I think about this sum becoming even. So this is one case. Now if we have one odd permutation and the other two even, no, that will not give me an even permutation. One odd does not work. Two odds and one even, yeah, that works. Alpha is even, but beta, gamma are both odd, or beta is even and or but, same thing, both odd, or gamma is even but alpha, beta are both odd. Zero odds, it works. Exactly one odd, that does not work. Two odds, that works. Three odds will not work. So these are all the possibilities. If and only if. Now we have to translate these into the integers r, s and t becoming even or odd, those things. So r, s and t are all even or, oh, wait, no, even, okay, are all odd. What am I saying? I hope what I have done here is correct. No, this case was much simpler. When alpha and beta needed to be even, we considered r and s to be odd. Okay, fine. So if these are all odd, or okay, alpha is even means r is odd but s and t are both even, okay, or s is odd but r and t are both even. So this case is quite different from the previous one. Whatever it is, we just have to find the truth, that's all. S is odd but r and t are both even, or t is odd but r and s are both even. Okay, so here we are getting all of them odd cycles. I mean, these are the lengths. So the lengths are all odd. So their sum is also odd because we have an odd number of odd numbers. So their sum is odd. Here we have two odd numbers, s and t. Their s plus t is even, but you take its sum with r, which is odd, you get odd. So that means in all these cases we are getting an odd sum. So we continue, if and only if r plus s plus t is odd. So let me just, because this thing is relatively much more complicated than the previous one, which we the previous one we understood much more clearly. So let us take an example. Particularly in this type of cases, S and T are both even. My only concern is that I hopefully have not written even in a place where I should have written odd, or vice versa. That is my only concern here. I hope everything has gone the way it is supposed to go. Let us now consider the case where S and T are even but R is odd. Let's just take this to be a 3 cycle. This to be, it's not necessary that we have to take disjoint cycles, even, and say 4, 5, 1, 8. Odd, even, even, odd, even, even. Now what about the evenness or oddness of this permutation? Since this is a 3 cycle, we can write it as a product of two cycles, 2 transpositions. This itself is a transposition, and this is a 4 cycle, so it can be written as a product of 3 transpositions. Okay. So in total, this entire product can be expressed as a product of how many transpositions? 2 plus 1 plus 3, 6 transpositions, and that 6, that number is even. So yes, in these cases we are getting an even. For example, this is an even permutation, and it's a product of 3 permutations which are all cycles. So our solution is okay. Next, let alpha and beta belong to Sn. Prove that alpha beta is even if and only if alpha and beta are both okay. Or both are both even or both odd. You must have noticed one thing, that this is what we used in the previous exercise precisely. So that means because we have been asked to prove this result is not being taken lightly. Lightly means it's a fundamental result, no? So if you want, you can modify this solution a little bit. What we have here, that this fact we have used in the previous solution. So after you have used it, you can write in brackets see the next solution. So that will justify its use there prematurely here. So it's a if and only if statement. There are two things to prove. If alpha and okay, we have already we have already proved in the solution to exercise 17 that if alpha and beta are both even, then alpha beta is also even. If alpha and beta are both even, and in fact that fact just follows from that theorem that the even permutations form a subgroup of the symmetric group. So we can refer to that theorem itself. Actually, there is nothing to write. You can understand the whole thing mentally also, but it's a solution, so we have to write something. Are both even, then so is alpha beta. By theorem 5-6. Let alpha and beta be both odd, then alpha is can be not write those transpositions and still express the thing like this, then alpha is a product of say P transpositions. And beta is a product of say Q transpositions. Where P and Q are odd positive integers. Because we ultimately need only the number of transpositions, not the transpositions themselves. Then alpha beta is a product of P plus Q transpositions. Since P plus Q is even, alpha beta is even. There are now I am noticing something. There are places where you can confuse yourself very easily. One such place, although this is not a very big problem, is we write things like this. No, since p plus q is even, so alpha plus alpha beta is even. This even and this even are two different things. This is the evenness of a positive integer, and this is the evenness of a permutations. They are entirely different notions. Another confusion is that you see here one may confuse oneself if one is not very careful. Say you have a permutation alpha. Alpha is defined to be even if it can be expressed as an even number of 2 cycles. That number of 2 cycles, if that is even, then alpha is even. If that number of 2 cycles is odd, then alpha is odd. This is the definition of evenness and oddness of a permutation. At the same time, if alpha is a cycle, say alpha is an n cycle, it's a cycle involving n symbols, then it is even if and only if that n is odd. Okay, so when you are applying the definition of evenness by expressing the permutation as a product of transpositions, then evenness directly corresponds to the evenness of that number of transpositions. Whereas if you are dealing with a cycle and just from the cycle length you want to say whether the the permutation is even or odd, then it is even if and only if the cycle length is odd. That is something entirely different. Okay. Okay, so since p plus q is even, alpha beta is even. So what have we proved here? Here we have proved that if both alpha and beta are even, then of course by our theorem alpha beta is even. And here in this part we have proved that if both of them are odd, then also alpha beta is even. Now the converse. Conversely, assume alpha beta is even. Now our aim is to prove that either both alpha and beta are even or both are odd permutations. Suppose that is not the case. That means one of these two things will happen. Alpha is even and beta is odd, or beta is even and alpha is odd. Suppose alpha is even and beta is odd, and we will derive a contradiction showing that this supposition is wrong. And beta is odd, then alpha is a product of say k transpositions. If you find it somewhat cumbersome to keep writing transpositions because it's a big word, you can just simply write a k2 cycles, product of k transpositions, and beta is a product of say L transpositions. where K and L are positive integers such that we are considering alpha to be even. So K is even and L is odd. Then alpha beta is a product of K plus L transpositions and now the contradiction will arise because K is even and L is odd, so the integer K plus L is odd since I need ink. Since K plus L is odd, alpha beta is odd, a contradiction. So our supposition is wrong. A similar contradiction arises from the supposition that alpha is odd but beta is even. So none of these two cases actually arises. Thus, we must have either both alpha and beta even or both odd. So that is the converse part, and we have proved the claim in the exercise. Then 20. So by now we know very well what happens when we multiply two permutations. I mean, what happens to their evenness or oddness, how they affect the evenness or oddness of the product. That's what we know. We have figured it out completely. Now next, associate an even permutation with the number +1 and an odd permutation with the number -1. With the number -1. Draw an analogy between the result of multiplying two permutations. Multiplying two permutations and the result of multiplying their corresponding numbers. Okay, so in this one, we are associating with an even permutation the number +1 and with an odd permutation the number -1. Let us make this association more mathematically rigorous using a function. We can do that. Let's just do like this. Let us define a function f from the symmetric group of degree n into this set consisting of these real numbers -1 and 1, and the definition of the function is this: f of sigma is equal to 1 if sigma is even and -1 if sigma is odd. We know that because we are mapping f, we are defining f from Sn into this, so sigma is coming from Sn, that is understood. So if sigma is an even permutation, its f image is defined to be 1, and if it is odd, then its f image is defined to be -1. Note that instead of writing note that, let us first take two permutations. Let sigma and tau belong to Sn. If both sigma and tau are even, then sigma composition tau is also even. And this fact can be expressed in terms of f like this. Hence, f of sigma composition tau, because this is also a permutation, it is also an element in Sn, so we can find its f image. This is equal to 1, and note that you can write 1 as 1 times 1, because both sigma and tau are even. So this one is f of sigma and this one is f of tau. If sigma is even but tau is odd, then sigma composition tau is odd. Hence, this time because it is odd, it is -1, and -1 can be written as 1 times -1. 1 is f of sigma, -1 is f of tau. If sigma is odd but tau is even, then sigma composition tau is again odd. Hence, f of sigma composition tau, like before, it is -1, and -1 can be written as -1 times 1. -1 is f of sigma because sigma now is odd, and 1 is f of tau because it is even. Finally, if both sigma and tau are odd, then sigma composition tau is even. Note that these things that we are directly writing, we have already seen in the previous, taking into account all the previous exercises, we are making these statements that when sigma and tau are even, both of them are even, then so is sigma composition tau, like that. Okay, so their justification lies before this exercise. Hence, it started raining heavily. F of sigma tau, composition tau is 1, because now this is even, but 1 can be written as minus 1 times minus 1, and this is equal to f of sigma f of tau. So you can see one thing happening. Sn is the group, the solution of course ends here, but you can notice one thing from this solution. Just like Sn is the group with respect to composition of mappings, this is also a small group under the operation which is ordinary multiplication of real numbers. And between these two groups we have a function like this, which somehow relates of course it relates the two sets, the elements of the two sets in this fashion, but more than that it relates the two binary operations. In what sense? Say this is your Sn and this is your this other group. Now you have two elements in Sn. We are not saying whether they are even or odd or whatever. They correspond to, each one of them corresponds to a number here. It may either be, in each case it is either 1 or minus 1 depending on whether sigma is even or odd. But the point is that if you do the calculation sigma composition tau in this group, then you get a third element sigma composition tau here in this group, right? Corresponding to this, you can treat this as a group and its mirror image in a sense, okay. It will not be exactly mirror image, but you can treat this one as a shadow of this group. So whatever you are doing in the actual world with sigma and tau, that has resulted in this new element sigma composition tau in the actual world, but the corresponding shadows also have interacted between themselves, and they have also produced another shadow. Now this function has the property that this thing which you have found in the shadow world using the shadows of these actual elements, this is nothing but the shadow of the result. So in this sense, f is keeping track of what is happening here, not just with the elements but with the binary operation, and projecting that entire thing in a sense on this much smaller shadow world. This type of functions are called homomorphisms. Homomorphism because between two similar type of structures, structure preserving maps. You have group on this side, you have group on this side also. Okay, so about which we will discuss, I mean it's coming, homomorphism, and let us end this discussion here itself. We are now going to continue with the ring exercises in this next video that is coming within an hour. So see you in that video.